Hi there, this is a quick video about exciting the atom, the first video we have on our new unit of atoms, nuclear energy and particle theory. And to start with, we're going to be thinking about what you remember about the atom from previous chemistry classes. Okay, so think back in time. What does it look like in your head? Does it look something like this? We have an atom which we can consider. In the middle we have a nucleus which contains neutrons and protons. And circling around that central nucleus we have negatively charged electrons, which are way, way smaller. So that might have been the image that you were thinking of. I hope so. Let's now consider some other features. So those electrons, do you remember anything about there being electron shells? There's a first shell which can hold 2 electrons, then a second shell, then a third shell. Now these shells are going to be kind of useful in what we're thinking about in a moment. But I'm just reminding you that there was an electron shell structure. Now, let's go through some discoveries now. What happened was there's this thing called emission spectra, which was noticed. It's noticed by a guy called Thomas Melville, and he was kind of like, it's really interesting that every single different gas gives off light at very specific wavelengths. And he saw that these spectra, these clear lines, you can see sodium lines really clear, mercury has a different set of lines, they all have individual sets of lines. And this spectrum became known as the line spectrum, because there's lines shown. It makes perfect sense there. Melville also noted that the line spectrum produced by a particular gas was always the same, so it was always consistent, so it was unique. That was the first bit of observing. It's kind of like, what's going to go on from here? Well, as we went a little bit further, we have something called absorption and emission lines. So if we had a continuum spectrum, let's say white light, which has all the colours of the rainbow, our first example shows that. Now, a hot gas gives out emission line spectrum, and we see clear lines being emitted by a certain hot gas. Now, if this was a cold gas and we had some white light behind it, we'd see absorption line spectra. And you see those lines are in the same place. So that means that when it's hot, it seems to emit light at certain wavelengths, and a cold gas seems to absorb lines at certain wavelengths. But again, they're matched up, so it's very much dependent on the type of gas. It's kind of like, well, how can we explain this? What's happening here? And that's the jump, and when we spoke about electron shells, that's what we were talking about. What happens, we discovered that electrons have very discrete energy levels, specific to a type of atom, which means that the jump from one shell to another has a certain amount of energy, and that certain amount of energy relates to a certain specific wavelength. So as we excite, it means that we absorb. So electrons drop in energy level, and that means light is going to be emitted. So they go from one level to another level, a lower level, and they then release that energy. And that is what we see with the emission lines. And then with the absorption lines, we see that when electrons gain an energy level, so they absorb some energy, then what happens here is that the light is absorbed and not emitted in this case. There's some formula relating to this. Physics is that way. So our first formula says that energy of a photon is directly proportional to its frequency. The frequency of the radiation tells us how much energy there is, multiplied by something known as Planck's constant, which is 6.63 times 10 to the minus 44 joules per second, which is also in our data booklet, so we don't have to worry about that. If we think about the wave equation, we can do a little bit more now, because we're talking about there being specific wavelengths. So if I rearrange my first formula and then recognize the speed of light is always going to be a constant, that'd be c, that I can see the wavelength equals Planck's constant multiplied by the speed of light divided by the energy of that photon. And these are the formulas we're going to use to be able to do some calculations. It's my quick overview, introduction to the atom, consideration of discrete energy levels, and also mention of the formulas you can be using. That is everything that you now need.